So in the first part of this lecture, we looked at building for the automobile in terms of factories. And I want to switch gears a little bit and talk about the massive construction projects that went into developing the network that allowed automobiles to traverse the countryside, both here in America and throughout the world. This coincided with the general kind of acceptance of the automobile as a part of society's fabric that happened after the turn of the century. Daimler and Benz produced automobiles mostly artisanally through the early 20th century. Other manufacturers, in particular those who had been producing stagecoaches or horse-drawn carriages or bicycles, began producing them as well. Ransom Olds was the first one to use mass production techniques, and that really made the automobile something beyond a luxury item, a sort of rarity. That began the process of turning the automobile into something that many people could afford. There's a sort of chicken and the egg problem, though, because roads, of course, are built for horses and horse carriages, and they're not necessarily built for horseless carriages or automobiles. Particularly the speeds that automobiles began to achieve, 20, 30 miles an hour by 1910, but also the way that the weight of an automobile is distributed onto its wheels is very different from that of a horse-drawn carriage. And automobiles, as we know today, require a harder pavement than something that's drawn by a horse. This led to new construction. The Long Island Motor Parkway was the first what's called a limited access highway. In other words, a road that's expressly designed for automobiles, automobile speeds, adopting the geometry of sort of longer curves and the need to separate pedestrian or horse traffic from automotive traffic. So overpasses in particular, but also ways to handle the grade separation that would come when one road crosses another without an intersection. The Long Island Parkway and its sort of twin, the Westchester Parkway, were also the first two to require payment to use the roads. It's expensive to build. You have to come up with some way to fund the construction, and both of these were ventures that relied on tolls being paid by people driving on them to pay not only for construction but also for maintenance. During World War I, a series of convoys across the United States, one of them including the future General and President Eisenhower, really highlighted the woeful condition of roads, at least as they might be used by automobiles in this country. There was concern that in wartime, the need to move troops or goods around the country quickly, the potential for that, at least in automobiles and trucks, as you see here, was being hindered by the fact that most roads were still dirt or gravel, often in pretty poor condition. And as you can see here on the right, one of these convoys trying to do a demonstration where they're driving across the country, bogged down in mud. Often these trucks would get stuck, or in some cases would overturn because of the poor conditions. The need for really hard paved infrastructure to take advantage of the internal combustion engine in the automobile would lead eventually to the American interstate highway system. But it would do so in sort of small steps. The first of these in 1923 was the so-called Lincoln Highway, a road that stretched from San Francisco to New York. And at first, this was largely kind of gravel roads. But when one of these convoys traversed it in the early 20s, it became clear that it would have to be hard paved to be useful. In 1922, after World War I, the military led the idea of a national highway infrastructure. And because it was sold as a way to ensure the national defense, there was plenty of federal money available. The federal government passed an act in 1921 that would match funds that states provided to build paved roads throughout the country, and a lot of this was used to build the so-called Pershing system, state highways, federal highways, mostly 2-lane, but some 4-lane roads, all of them with a hard surface, usually blacktop, although eventually concrete. By 1939, especially after several years of Works Project administration work, the Roosevelt administration planned for what they called superhighways. These you see here in the lower drawing by 1944 suggested that they would accommodate automobiles at much higher speeds. So there would be consistent grade separations, exit ramps, and maybe most importantly, median strips separating traffic going in 2 directions. You can see here the anticipated traffic that they thought there would be, and the original plan was literally for 8 of these, one of which would sort of parallel the Lincoln Highway, but others would connect Chicago and Detroit to the East Coast, would take the eastern seaboard that we're familiar with and provide it with these superhighways, but would also connect to the West Coast, to California, Seattle, the developing cities out there. Other countries at about the same time followed similar processes. Germany's maybe is most famous. The Autobahn, which started construction in 1936, really pushed this idea of the limited access. In other words, making sure that the superhighways were always available for high-speed traffic by taking any other traffic, any other roads, and grade separating them with bridges or underpasses. Finally, after World War II, the Federal Highway Act of 1956 proposed that limited access highways be built connecting every American city that had more than 50,000 residents. The idea was that these would all be 4-lane, they would all be limited access. This was clearly inspired by the German Autobahn, and it was finally completed, but not until 1992, and at a cost overall of nearly $500 billion. Nevertheless, the interstate highway system, as expensive as it was crucial to the economy of the post-war United States. It not only linked all of the major cities and eventually even most of the minor ones, it also produced these kind of arteries of commerce where towns would actually grow along the highways. At the time, this was seen as a really positive thing. It went hand in hand with the then very popular idea of slum clearance, taking the least attractive housing or the least attractive neighborhoods, clearing those out and replacing them with these clear highways. That, of course, we know in hindsight, very often cleared out African American neighborhoods, or neighborhoods that, just because they had substandard housing, were no less vital than other neighborhoods in other cities. Today, you can almost track where African American or poor neighborhoods were in a lot of American cities just by looking at the kind of scars left by highway development. Limited access also meant that the highway system had a huge appetite for land. Building, for instance, a cloverleaf intersection that you see here to allow one limited access highway to cross another required acres and acres of cut and fill, which in turn required extensive deforestation in these localized areas. Here on the left, you see a construction photo of one of these interstate highways in Kansas City. You can see how much territory it's cleared out of the area near downtown. And on the right, you see maybe one of the most notorious examples of these, the neighborhood of Overtown in Miami, which in 1955 was a poor but nevertheless kind of vital African-American neighborhood. You can see that by 1980, the interstate has gobbled up an awful lot of that neighborhood's housing, but also a lot of what we might call its social or cultural infrastructure. And even though the interstate highway system was, as I said, vital to the way the American economy grew, it was not without its costs. And often the poorest residents of a city, certainly residents of color in American cities, bore the brunt of the impact of much of this construction. The interstate highway system developed from a system of tollways that states built themselves. And the most famous of these, the earliest of these, was the Pennsylvania Turnpike, which was built between 1938 and 1954 with a break, obviously, for World War II. The Pennsylvania Turnpike was designed to provide automobile access through some of the toughest terrain on the East Coast. The mountains of Pennsylvania had sort of resisted building roads that people could actually use. And the state realized that if it was to bring some of the economic benefits, particularly after World War II, of the boom that was going on in the country, it was going to have to find a way to get goods and services to a lot of these more remote parts of the state. The Turnpike involved a lot of tunneling through mountains, a lot of bridging over valleys, and gave not only the state of Pennsylvania, but the country a lot of its early experience in building for these higher speed, limited access highways. A lot of what went into the Pennsylvania Turnpike was bridge design. And as the road network, first in terms of the kind of Federal Highway Act buildings or construction projects in the 20s, and then eventually the interstate highways in the 50s and 60s grew, they built on a kind of growing tradition of bridge construction. And I want to look at the way that American bridge design evolved in this period, going from bridges that initially are used for kind of horse and carriages to bridges that can accommodate the faster and in a lot of cases much heavier traffic that the interstate highway system provided. I want to look at these three figures. There's a kind of lineage between the three that I think you can describe as a sort of American approach to bridge design. It starts in Germany with a German emigre, Gustav Lindenthal, who came to the United States in 1874, first as a stonemason, and he worked his way up through construction projects, finally as an engineer for railroads, finally in 1874 opening his own engineering practice. Another emigre, Othmar Ammann, who was born in Switzerland, educated in Switzerland, so in the same kind of milieu as Robert Maillard, worked with Lindenthal on one of his crucial projects that we'll take a look at here in a minute, Hell Gate. He ended up being the key bridge engineer in New York City. He worked for the Port of New York, a sort of quasi-governmental organization that had the authority to build infrastructure within the city of New York, not only the port facilities, but also roads and even eventually airports. The two of them have this interesting moment where they both propose kind of the world's longest bridges over the Hudson. Ammann wins, and this is one of the ways that he sort of cements his authority as the bridge designer for New York's massive construction era in the post-war, after World War II. He founds this firm of not just bridge engineers, but long-span engineers in general, Ammann and Whitney, in 1945, and they really become the kind of go-to firm for infrastructure projects of all types in the post-war era. Those two are sort of, in some ways, like very pure engineers, although, as we'll see, they have interests in bridge aesthetics. David Steinman, who is a Lindenthal employee during World War I, is another key figure who concentrates as much on bridge aesthetics as he does on bridge engineering. He and Ammann are sort of at odds over the role of aesthetics in bridge design, and I want to look a little bit at their works to get at how this idea of kind of structural art impacts not only skyscrapers, some of which we've looked at, but bridge design in the 20th century. So to start with, Lindenthal as a German emigre is sort of trained in German engineering, And his designs for bridges reflect, as you can see, a very kind of 19th century German style, if you look at the towers at the ends. But also what we might think of as a sort of polytechnic approach to engineering, that these are mathematical problems that get solved in the most efficient way possible. And after that, you sort of add on ornament if you want to make it into a sort of civic monument. Here, this bridge in Pittsburgh is a lenticular bridge. We've seen one of these before when we were looking at railway design. There's a compression arch at the top, a tension arch at the bottom, and the advantage to this is that the thrusts of the two more or less balance one another out. And so you don't need the kind of massive backspans that you need on a suspension bridge. You do, however, need a tower that holds the connection point up. And Lindenthal sort of chooses to decorate this in a very sort of Germanic style, appropriate for Pittsburgh, which is full of German emigres in 1883. There's a kind of science to bridge design that looks at typology and the fact that there are certain types of structure that are appropriate for certain spans. This is a diagram by an engineer that we'll come to talk about when we look at post-war skyscrapers, Myron Goldsmith, who, in arguing for his approach to skyscraper design, looks at bridge design first and says, if you are designing a bridge span that's 500 or 600 feet, the cheapest, most effective way to do this is a simple truss. But as that span gets longer and longer, different types of structure end up being either more efficient or at some point the only possible way to solve a given span. By the time you get up over sort of 2,000 feet, Goldsmith recognizes, as do lots of bridge engineers, that you can't handle that with, say, a simple girder bridge, right? The dead weight of the girder ends up being more than the girder can actually carry at those spans. So you have to switch typology, right? And one way to think of this is that changes in quantity end up leading to changes in quality, that you have to come with a different approach to the problem as the spans get larger and larger. And Lindenthal does this. There are bridges that he designs for automotive, but also some rail traffic in New York at the end of the 19th and beginning of the 20th century that show this. So the Queensboro Bridge on the left is a cantilever bridge, and Lindenthal is able to do this, he argues, because there's an island in the middle of the river where the bridge is crossing. So it makes perfect sense to build towers on the island and to cantilever the bridge out from those two towers. You get a good sense here in the construction photo for how a cantilever bridge works. And it may remind you of the Eads Bridge in St. Louis while it was being constructed, right? That there are sort of tensile elements on top, compression elements on the bottom, and you can imagine the bridge sort of growing out from its towers as these very, very long cantilevers until they finally connect with similar spans coming from the shore. If you have to go across the East River in one big span, however, Lindenthal recognizes that that requires a suspension bridge. There's no other way to do it. And so here, just north of the Brooklyn Bridge, Lindenthal offers his own kind of take on the suspension bridge, both in terms of engineering and in terms of aesthetics. It's interesting to note that this is now like a generation beyond the Brooklyn Bridge, and steel is clearly the most economical choice rather than stone. The towers, the compression towers that support the cables of the Manhattan Bridge are all in steel, all in express steel. And there's none of the kind of fiddling around with Gothic arches or anything that Roebling did on the Brooklyn Bridge. Here is a bridge that really kind of speaks to the materials and the structural type that's being used. Here you see the finished product. The Queensboro Bridge, Lindenthal thought, ended up looking overly heavy. Today, I think we look at it and think of it as almost sort of a period piece for just how much kind of steel there is to it. But it's an effective way of bridging kind of two channels with an island in the middle, right? The cantilevers get a little bit lost, but once you've seen the construction photo, you can understand how the bridge works. The Manhattan Bridge, Lindenthal thought, was a much purer expression, right? That you're seeing very clearly how the bridge stands up, how the deck is carried by the cables, and how the towers are balanced by the backspan. Interestingly, when Lindenthal had to build a rail bridge, right, we talked about the fact that because locomotives in particular are so heavy, and because they're limited in the slope that they can maintain, the suspension bridge really doesn't work for railroads. And when Lindenthal has to design a rail bridge, as he does for Hell Gate, which takes 10 years to build in the early 20th century, he reverts to the much stiffer arch form. This is a two-hinged arch. You can see that it carries the rail deck below on cables. On the right, you can see the construction shot, and this again will remind you maybe of Eads Bridge, where the arches are being held by temporary tension elements, or the arch halves are being held by temporary tension elements until they can get connected in the middle. You can see that the construction technology has really changed. These are climber cranes that come out and literally kind of build the bridge as they walk out to the edge of the finished construction. And you can also see that very much like the finials on a flying buttress in Gothic construction, these massive stone piers at the end of the arch are designed to take the natural thrust of the relatively shallow arch in this case, and to help direct those into the foundations. It's what's called a two-hinged arch. If you remember the Galerie des Machines in Paris, the three-hinged arch, this only has two. They're both at the junction between the arch and the foundations, and the weights, the stone piers there are designed to help resist the thrust of those pins and turn those down again into the foundations. Lindenthal proposes a bridge over the Hudson River in the late 19th century that would be by far the largest span bridge in the world, right? Over 2,800 feet, almost 3,000 feet. And he publishes this both in the local papers and in Scientific American, and says that this will help New York's economy because it will connect the kind of suburbs of New Jersey, which at the time are only accessible by ferry boat. You can see that Lindenthal's scheme calls for this enormously kind of heavy pair of towers and this cable, this trussed cable that supports the deck. Lindenthal here is comparing it, interestingly, with two bridges that we've seen before, the New York-Brooklyn Bridge, called the Brooklyn Bridge today, almost twice the main span of that, and the Firth of Forth Bridge, which you'll notice he says is in process of erection, right? So this is the same time as the Firth of Forth. His kind of pupil, Othmar Ammann, is the one who ends up designing and building the Hudson River Bridge. He does it about 10 miles further north, where the span is much less, and he's able to do it with a much simpler set of cables and decks. The George Washington Bridge is Ammann's sort of signature work. It gets built as the Depression is taking hold. It's a public project. It's not yet a Works Progress Administration project. And you can see the finished product is very much like the Manhattan Bridge, a kind of essay in exposed steelwork. Right? It's remarked upon by many that it's got a kind of beauty to it that comes from its expression. Here is Corbusier talking about it in the 30s or 40s. Says it's the most beautiful bridge in the world because its cables and steel beams very clearly are a reversed arch, right? It shows off its catenary structure very, very clearly. You see nothing but the bent cords supported by the two steel towers. And here he says steel architecture seems to laugh, right? He's talking about the expression of the material as being very, very sort of pure. What Corbusier didn't maybe understand was that the original scheme for the George Washington Bridge would have made it look very much like the Brooklyn Bridge, would have clad those steel towers in a stone skin, and not just that, but a stone like neoclassical skin, right? This is Ammann's original sketch, and the only reason that the stone doesn't get put on is that in the Depression, the city can't afford the kind of ornamental cladding that goes around the skeleton. Ammann never meant for the steel skeleton to actually be shown. there's an interesting kind of moment here, right, in bridge aesthetics, where do we design the bridge as a civic monument, dress it up in the language that we understand in the 20s to be the sort of acceptable form of a government or a public structure, which is still 2,000 years later a kind of Roman classicism? Or, as Corbusier is arguing when he looks at the bridge, do we let infrastructure speak for itself? Do we find kind of new ways of perceiving beauty or new standards of beauty in the kind of nuts and bolts of how these things actually work? Ammann maybe learns his lesson a little bit, and in his subsequent work, highway bridges, a couple of which are built for the developing interstate highway system, he actually does let the steel speak for itself. The Bayonne Bridge here, a large twin arch, or two-pin steel arch, a little bit like Hell Gate. You can see that here it's the deck itself that's actually providing the compression, and the steelwork is speaking very plainly, right? There's none of the kind of stone that his former boss Lindenthal used in Hell Gate. Here the deck of the bridge is being used for its dead weight to help direct the force of the arch into the foundations. And then when Ammann designs two suspension bridges between Long Island and the mainland, or Long Island and the mainland in one case, and Long Island and Staten Island in the other, he lets the towers and the cables speak very clearly. He does not show off all of the kind of cross-bracing that he did on the George Washington Bridge. He clads those, but he clads them in steel. And there are little things that people quibble with. The round arches, for instance, don't necessarily, that's not necessarily required. Ammann here is using very simple forms in steel as a way to emphasize the bridge as a gateway, right? A subtle aesthetic choice, but an aesthetic choice nonetheless. And the final engineer designer that I want to look at in terms of bridge design is David Steinman. And Steinman comes out of Lindenthal's office, but he senses the kind of poetic potential of bridges, especially suspension bridges, more so than Ammann or Lindenthal do. And when he gets the commission for a suspension bridge, this is a relatively small one in Portland, Oregon, he looks not to the kind of neoclassical examples that Ammann did in his original scheme for George Washington. He thinks of the bridge essentially as a kind of translation of Gothic principles, of Gothic structure. And so here, the St. John's Bridge, the towers have to hold the cables up, but they have to be sort of self-braced. And Steinman chooses kind of Gothic shapes, pointed arches, as a reference, an aesthetic reference. The towers can be kind of any shape they want so long as they're braced with one another. Steinman chooses the Gothic as a kind of callback to what he thinks of as the purest structural legacy. Steinman does other bridges as well, some of which adopt a slightly more straightforward approach. So this is a bridge over a channel in Rhode Island, slightly bigger scale than St. John's, but nevertheless similar principles. And here the Gothic, the pointed arch, is almost hidden, right? It comes out of the cross bracing that is a slightly purer expression of what the bridge tower needs to do. The cross bracing is there to prevent it from side sway, and the Gothic arch that you see there is derived from the thickening of the cross bracing in one place as it approaches the towers. Steinman is also kind of an aesthetician or a philosopher, and alongside his engineering, he is really interested in thinking through what the aesthetics want to be. He says that some of this has to come out of analysis and the idea of efficiency, right? A suspension bridge can't get dressed up too much because weight is really crucial, so there's only so much that you can do. He says, though, that now that we know where the metal needs to get placed, as he puts it, we can eliminate some of the massive and clumsy designs of the past. And you might think of some of the kind of early railroad bridges that we looked at in particular as being workable, but using more material than are necessary given modern engineering standards. Steel, he says, and here I think he's thinking of Lindenthal, were originally built along strictly utilitarian lines. And he thinks of things like the Smithfield Street Bridge as awkward or aesthetically kind of unpleasing. And adding filigree, ornament, decorative details to the structural principle, as Lindenthal did, he thinks is a mistake. He thinks that the development of structural forms, inherently beautiful, into forms that resonate with our aesthetic traditions, so stretching the suspension bridge proportions kind of into a Gothic arch, is a way to achieve a kind of new synthesis of beauty, right? That's taking the efficiency and the beautiful forms that come out of a sort of pure approach to efficiency, marrying them to some of the traditions that we have, and finding ways to make steel, which he thinks is the ultimate bridge material, resonate with those is the way that he thinks we're going to get to a structural art, right? A true structural art where aesthetics are coming out of an understanding of the problem, of the material, but also of some of the traditions that we're in. A lot of these ideas come together in the greatest kind of bridge project in America, a Depression era project that uses a lot of public funding to put a lot of people to work. And to make an important, but in the scheme of things, like slightly minor economic link between San Francisco and the suburbs on the North Bay. The Golden Gate Bridge gets its start in 1933 with ideas about how to span what's not only a colossal opening, right, something like 4,000 feet of total span, but also a truly difficult area because the Golden Gate is so full of kind of bad weather, right? Winds and things like that. There's a lot of thought about how the construction has to proceed, and in particular, how construction can proceed without interfering with shipping traffic underneath. The original scheme for the bridge that you see here is what Steinman would have referred to as an unnecessarily angular or a really heavy-handed approach to the problem, right? A combination of cantilever and suspension bridge that the engineers initially come up with as what they see as the only way to get across the whole span. Joseph Strauss is the engineer who finally says no, that this is maybe at the limits of what suspension technology can do at the time, but it's at the limits, right? It's something that is relatively achievable. You see all the pieces that we've seen before in suspension bridges, so the compression towers that go into foundations, in one case on land, in the other case in a cofferdam that's built to get the foundations down to bedrock. You can see that there are massive anchorages on both sides. And one additional complication on the San Francisco side, there's an historic fort that the roadway has to sort of jump across. And so in addition to the 4,000-foot suspension span, there's a couple 100-foot arch span that has to be integrated with this. Strauss is very much in the kind of Steinman camp of bridge aesthetics. He thinks that the ultimate form of the bridge has to express the basic principles of what a suspension bridge is doing, but also to show off what steel can do, the kind of tenuous proportions. He thinks, though, that those proportions can get tweaked here and there to emphasize what the piece is doing. So even though the cables and the deck are kind of very pure structural steel forms, the towers themselves, Strauss spends a lot of time on little ornamental, like punctuation. So these vertical kind of stripes on the crossbars, the proportions of those crossbars versus the voids below them as they go up, and the way that the towers kind of narrow in proportions as they get toward the top. Some of that is structurally necessary. The towers have to be braced internally. Yes, you can use less steel as you get up toward the top of the towers, but a lot of them I think are very subtle visual proportions. Strauss is not interested in building a Gothic bridge as Steinman was, but he is interested in building a bridge that not only accomplishes the task of spanning the Golden Gate, but also speaks to kind of what it's doing. And today that bridge is iconic, right? It's one of these structures that we see so often that maybe we don't look at as closely as we should. But if you look at the way the voids in the towers are proportioned, if you look at the way that the crossbars are sort of fared into the the towers as they come down. If you look at the vertical kind of stripes on the sides of the towers, what you realize is that there are all of these little tricks, right? The vertical stripes on the side remind me a little bit of the I-beams on Mies van der Rohe's buildings that we'll look at when we look at skyscrapers, right? Emphasizing the vertical reach of the towers while providing little shadow lines that give it almost like kind of pinstriping. The bridge's color is demanded by the Coast Guard. They want the bridge to be orange so it contrasts with the fog, but that too has really become part of the bridge's aesthetics. It's an important project too because of its labor implications. Over those 4 years, it puts literally thousands of people to work. And even though there are a series of fatal accidents, not surprising on a bridge this size, it also develops a reputation for setting new standards in safety on construction sites. All of these become important not only through the Depression, but they'll become important also after World War II. And finally, the Golden Gate sets new standards for both the scale of the span and for the kind of slenderness of the deck. The truss that you see there comes after an event that happens when Moisseiff, one of the engineers on the Golden Gate Bridge, is hired by the state of Washington to build a slightly smaller suspension bridge over the Tacoma Narrows. And the Tacoma Narrows Bridge beats the Golden Gate in the slenderness of its deck, the kind of elegance of its towers, and the thinness of its cables. But these end up being the sort of beyond the limits of suspension bridge technology, beyond the limits of steel construction. Very quickly after the Tacoma Narrows Bridge opens, it gets commentary for the liveliness of its deck, particularly when the wind starts to pick up. The deck heaves up and down in windstorms. And this is, today we look at this and we realize that yes, of course, right, a deck that narrow is going to experience uplift, suspension bridges being flexible. If the wind is just at the right sort of frequency, the bridge is going to rise and fall in ways that we think of now as harmonic motion. None of this is evident to the bridge designers of the era, however, and the Tacoma Narrows is a prime example of engineers learning from failure. This solution is a great gravity solution. Reduce the weight of the deck, make the deck as skinny and as light as possible. And you need smaller towers, therefore smaller foundations. But it gets at a problem that the engineers of the time wouldn't have known about or wouldn't have understood, which is the way that these slender bridges perform in the wind. We'll end this part of the lecture with this famous, maybe the most famous film footage in civil engineering history. This is the Tacoma Narrows at the end of its life in a windstorm of about 35, 40 miles an hour. The bridge gets closed by the authorities. Engineers get called out to advise on what to do both immediately in the windstorm, but also how to fix it. And as you'll see as the film goes on, the bridge ends up failing in the windstorm. And from this, engineers understand that decks in suspension bridges have to be designed not only to resist gravity, but also to resist the uplift of wind, and in this case, to be stiff enough to resist the tendency of bridges to behave harmonically. Deeper trusses that stiffen the bridges. Occasionally you see bridges now with tie downs that are designed to prevent this from happening. You'll see Moisseiff himself walking off the bridge. No one was injured or killed in the bridge failure. They had evacuated the bridge in plenty of time. But as you'll see, that car is not long for this world. We'll pick up in the third section of the lecture with a different type of internal combustion and building for not only a different scale, but a whole different quality of travel. And I'll leave you with the Tacoma Narrows in its final moments.